Imagine this, learner. You're overseeing a massive industrial complex, maybe a petrochemical refinery or a critical marine vessel far out at sea. Suddenly, there's an incident. A large storage tank, or maybe a vital section of a ship, is just engulfed in an inferno. You know instinctively that water alone won't cut it. Against certain fuels or chemicals, it might even, make things worse. In these high-stakes, really terrifying situations, you need more than just brute force. You need something specialized, something that could rapidly smother the flames, cut off the oxygen, and provide a lasting blanket of protection. You need foam. Welcome to a deep dive into the foundational document that dictates precisely how we deploy this specialized solution to fight those incredibly challenging fires. NFPA 11, the standard for low, medium, and high expansion foam systems and compressed air foam systems. Now, this isn't about dry technical specifications, though we'll certainly uncover some truly ingenious engineering details. Our mission today is to cut through the complexity, to give you a genuine shortcut to being well-informed about the critical role these standards play in property protection, how they're constantly evolving with new technologies, and some surprising facts about fire safety foam, including its profound and frankly undeniable environmental impact, which is currently driving a seismic shift across the industry.
And our guide for this deep dive is none other than the comprehensive 2021 edition of NFPA 11 itself. This isn't just some manual, it's really the authoritative standard that shapes fire protection systems worldwide. It's a living document, full of insights into how we safeguard our most vulnerable assets.
Okay, let's unpack this. For someone who might interact with industrial safety or design, but isn't necessarily a fire protection engineer day in, day out.
Right.
What exactly is NFPA 11? Why is it such a cornerstone document in fire safety?
Right. Well, at its core, NFPA 11 is the essential blueprint for the entire life cycle of foam fire protection systems. It covers the design, installation, operation, testing, and maintenance of low, medium, and high expansion and compressed air foam systems for fire protection. That's actually straight from Section 1.1.1 of the standard itself.
Okay, design, install, operate, test, maintain. Pretty much the whole package.
Exactly. So whether we're talking about a massive fixed system over a fuel depot, or maybe a semi-fixed system for a particular process area, or even portable units for specific hazards, NFPA 11 provides that comprehensive guidance. It's essentially the rulebook. It's there to ensure these complex, life-saving systems not only work, but work correctly when that critical moment arrives.
It sounds incredibly thorough. But, given how comprehensive it is, it's easy to assume it covers absolutely everything. Where does it draw its boundaries? Are there particular areas of fire protection it intentionally leaves to other specialized standards? And why is that distinction so crucial?
That's an excellent, really insightful question, because understanding its limitations is just as important as understanding its scope. NFPA 11 is actually quite clear about what it doesn't do. For instance, it explicitly says it is not the intent of this standard to specify where foam protection is required.
Okay, so it tells you how, but not if you need it somewhere.
Precisely. This is a critical distinction. It tells you how to design and install a foam system, but not when or where one is absolutely mandated. That decision typically falls to other codes, risk assessments, that kind of thing.
Right.
Furthermore, its primary purpose, stated right there in 1.2.3, is explicitly property protection and not life safety.
Interesting distinction. Property protection first.
Mm-hmm. Now, obviously, fire protection inherently contributes to life safety, but the direct focus of NFPA 11's provisions is safeguarding assets. It also explicitly clarifies several types of systems it's not applicable to, things like older chemical foams, which are now considered obsolete,
Okay.
combined agent systems too, mobile foam apparatus, fire trucks with foam, they fall under NFPA 1901, or Class A foam and systems which are used for ordinary combustibles like wood or paper. Those are detailed in NFPA 1150. So these distinctions are really vital for professionals, guiding them to the correct specialized standard for whatever situation they're facing.
Okay, here's where it gets really interesting and frankly a little surprising for some people. The NFPA itself issues some notably strong disclaimers about its own standards. I mean, they create these critical safety documents, the gold standard for many, yet they're incredibly upfront about limits to their liability and responsibility. What's the thinking behind that? What are the practical implications for someone relying on these standards?
Yeah, what's truly fascinating here is the sheer level of transparency and the explicit disclaimers the NFPA provides. You often find them right in the front matter of the document. They plainly disclaim liability for any personal injury, property, or other damages arising from the use or reliance on their standards. That's from PBORT 1. They also make no guarantee or warranty as to the accuracy or completeness of any information published. Also, P1.
Wow, okay. No guarantees.
It's a stark reminder, really. Even with the most rigorously developed standards put together by a vast consensus process, there's always an element of professional judgment and responsibility that rests with the end user.
So for an engineer on the ground, maybe a facility manager needing to ensure compliance, does this mean they essentially need to, I don't know, audit the standard themselves,
Yeah.
even while relying on it? It sounds like it places a significant burden on the user.
Precisely. The NFPA clarifies that it's not undertaking to render professional or other services, nor to perform any duty owed by any person or entity to someone else. Again, P1. This means you, as the user, should rely on his or her own independent judgment or seek the advice of a competent professional. That's also in P1.
So critical thinking required.
Absolutely. It isn't a set it and forget it situation where just following the text guarantees perfect outcomes. It demands active engagement and critical thought. Furthermore, the NFPA explicitly states it has no power, nor does it undertake, to police or enforce compliance, and it does not list, certify, test, or inspect products, designs, or installations for compliance. That's all from P1.
So they write the rules, but they don't enforce them or check if you follow them.
Correct. Any certification of compliance, therefore, is solely the responsibility of the certifier or the maker of the statement. This clearly places significant responsibility on the authority. Having jurisdiction, or AHJ, that could be a fire marshal, a building official, maybe even the property owner themselves in some cases. And, of course, the professionals implementing the standard. They have to apply due diligence, expertise, and independent judgment. It's a constant reminder that even the best standards require critical thinking because every site, every hazard is, well, unique. And, if we connect this to the bigger picture, you'll see just how dynamic and constantly evolving these standards truly are. NFPA standards aren't static documents. They are living, breathing guidelines. They may be superseded at any time by the issuance of a new edition, may be amended with the issuance of tentative interim amendments, TIAs, or be corrected by errata. That's from P.2.
TIAs and errata. So constant updates.
Exactly. This continuous revision process is absolutely crucial because it ensures that participants in the NFPA standards development process consider the then current and available information on incidents, materials, technologies, innovations, and methods as these develop over time, and that NFPA standards reflect this consideration. Also, P.2. It's really a testament to the fact that fire science, technology, and our understanding of risk are always advancing.
So what does this all mean for someone relying on these standards? Does it mean you always need the absolute latest version, or can you sort of get by with an older one for a while?
You absolutely need the most current version. The NFPA unequivocally encourages the use of the most current edition, P.2, again, because, as they state, any previous edition no longer represents the current NFPA standard.
Right.
Using an outdated standard isn't just a minor oversight. It could mean you're missing critical updates, new safety protocols, or, advancements in technology, things that could literally mean the difference between effective suppression and, well, catastrophic failure. The stakes are just too high to not stay current.
That makes perfect sense. Given this relentless pace of evolution, instead of just rattling off dates and minor changes, let's maybe trace the major trends and turning points in NFPA 11's history. What were the big forces that reshaped it over the decades?
Oh, it's quite a story of adaptation, really. It mirrors the broader evolution of fire protection itself. Early editions, like the 1983 edition, saw a significant rewrite. It consolidated material that had previously been in NFPA 11B, which focused on synthetic and combined agent systems.
Bringing things together.
Yeah, exactly. That was a major push towards unifying disparate guidelines, making it easier for practitioners to find comprehensive information in one place.
So an initial focus on consolidation for clarity and usability. And after that, how did the standard continue to adapt?
Well, subsequent revisions often focused on refining that clarity. The 1994 revision, for example, specifically worked to separate mandatory requirements from advisory text.
Okay, the shall versus the should.
Exactly. Sounds minor, but it's incredibly important for interpretation and enforcement. Then, as the world became more interconnected, new concerns emerged. The 1998 edition significantly expanded its scope to include foam systems for marine applications.
Oh, the maritime world. Big challenges there.
Huge challenges, reflecting the unique and often harrowing challenges of fire protection at sea. And crucially, it also began to address the environmental impact of foam system discharges.
Back in '98, that seems quite forward-thinking.
It was, recognizing a different kind of threat beyond just the flames. And that theme, as we'll discuss, has only grown in importance. It's become one of the most pressing issues in the industry today.
Okay, so environmental concerns were entering the picture. How did new technologies and system types start getting woven into the fabric of NFPA 11?
Well, the early 2000s saw a focus on integrating different foam systems more seamlessly. The 2002 edition refined requirements for mixing foam concentrates, clarified rules for foam concentrate pumps. It also integrated medium and high expansion foam systems more fully, acknowledging their growing use for things like total flooding.
Total flooding, right? Filling
Ooh.
whole rooms.
Just a few years later, the 2005 edition further reorganized the standard to better incorporate requirements for low, medium, and high expansion foam, building on the framework of NFPA 11A. This made the standard much more fluid and comprehensive across all the main foam types.
I recall hearing a lot about compressed air foam systems, or CFS, becoming more prevalent in firefighting around then. When did that breakthrough technology get formally recognized in NFPA 11?
Ah, yes, CIFS. That was a significant moment. The 2010 edition introduced a whole new chapter dedicated to compressed air foam
A
system.
whole chapter just for CFS.
Yep. Recognizing their distinct application methods and benefits. It also refined terminology to comply with NFPA's Manual of Style, ensuring greater consistency and clarity across all their documents. Then, the 2016 edition continued this trend of practical refinement. It addressed several areas of concern: reorganization of piping requirements, setting acceptance criteria for annual concentrate testing. It also promoted environmentally friendly testing methods for proportioners, and even permitted seal-only protection for specific composite roofs, things like that.
So getting really granular based on field experience.
Exactly. Highlighting the ongoing granular refinements based on real-world field experience and new material sciences.
And now our current focus, the 2021 edition. It sounds like this version brought truly significant changes, reflecting some major industry shifts. What were the big defining updates here?
Oh, the 2021 edition brought about truly transformative changes, driven by both technological advancements and, frankly, a growing environmental consciousness. First, there were multiple revisions regarding the use of synthetic fluorine-free foam, or SFFF, including a brand new definition.
SFFF. That's the big one everyone's talking about.
It really is. This is a direct, urgent response to the environmental and health concerns related to legacy fluorinated compounds. The PFAS issue, a topic we'll definitely explore in depth. New definitions and explanatory annex material were also provided for cone roofs and external floating roofs, enhancing clarity for tank protection. That was needed. And a key operational shift was the deletion of specific foam types listed for hydrocarbon fuels in Chapter 4. Now, all foams are strictly required to be listed for the specific liquid they protect.
So no more general recommendations. It has to be listed for that specific fuel.
Precisely. It places a much greater burden on manufacturers and users to ensure precise compatibility. It's all about documented proof now.
That's a critical shift. More precision required.
Absolutely. This edition also updated metric conversions for better usability, a small but important detail for global application. But perhaps one of the most substantial structural changes was the consolidation of requirements from NFPA 16.
NFPA 16, that was for foam water sprinklers.
That's right, standard for the installation of foam water sprinkler and foam water spray systems. Those requirements were merged into a new Chapter 6 of NFPA 11. This streamlines the information, making NFPA 11 an even more comprehensive resource for foam system design. Basically a one-stop shop for most foam systems now.
So bringing other relevant standards directly into NFPA 11 for a more holistic resource makes sense. What about the ongoing reliability of these incredibly complex systems once they're installed?
Good question. For that, the 2021 edition brought significantly enhanced maintenance requirements. A whole new Chapter 13 now provides more comprehensive guidelines for inspection, testing, and maintenance, including much clearer minimum frequencies.
Chapter 13, IPM inspection, testing, maintenance, crucial.
Absolutely essential for ensuring long-term operational readiness and reliability. And, to support the industry's rapid shift, a new Annex H offers summaries of current research and testing specifically for SFFF. Finally, a new Annex I outlines a testing protocol specifically for rim seal fires in non-metallic floating roof structures.
Wow, very specific. Non-metallic roofs.
Exactly, showcasing the depth of specialized application needs and reflecting the continuous need to adapt to new materials and construction methods. The continuous updating really highlights a living document that constantly adapts to new knowledge, new challenges, and perhaps most importantly, new scientific understanding of both fire suppression and environmental impact. Hashtag the chemistry and mechanics of foam firefighting.
Okay, let's dive into the core ingredient. Foam concentrate. When we talk about foam, it can't just be, soap and water, right?
Yeah.
What exactly is in these concentrates, and why are there so many specialized types?
Right. What's truly fascinating here is that foam concentrate is indeed far more complex than just soap and water. These are meticulously engineered chemical solutions designed for very specific purposes. Foam concentrates are rigorously classified by their chemical composition, their use percentage for dilution, their minimum usable temperature, and critically, the fuels on which the concentrate is effective.
Okay, chemistry, percentage, temperature, fuel type. Lots of variables.
Exactly. This isn't a one-size-fits-all solution. Choosing the right foam depends entirely on the specific fire hazard you're facing. Trying to use the wrong type of foam can be just as ineffective or even worse than using water on, say, a gasoline fire.
So let's break down these major categories. What are the key types of concentrates, and what makes each one uniquely suited for particular challenges?
Okay, let's explore the major players. First, we have protein foam concentrate. As the name suggests, it's derived primarily from protein hydrolysate.
Protein, like from animal sources.
Often, yes.
Okay.
Fortified with stabilizing additives and inhibitors to protect against freezing, corrosion, bacterial decomposition, and to control viscosity. These are typically diluted to 3–6% solutions and are compatible with certain dry chemicals. They create a very tough, stable, and heat-resistant foam blanket. It's really about forming a strong physical barrier to the fire.
Okay, tough and stable. What's next?
Next, there's fluoroprotein foam concentrate. This is similar to protein foam, but with the crucial addition of a synthetic fluorinated surfactant.
Ah, the fluoro part. That's where the PFAS comes in, right?
Traditionally, yes. This additive significantly improves its resistance to fuel pickup, meaning the foam blanket is less likely to become contaminated and break down when it's sitting on top of the burning fuel. Like protein foam, it's also typically diluted to 3–6% solutions and is compatible with some dry chemicals.
Got it. Better fuel resistance
Yeah.
than AFFF.
Right. Aqueous film-forming foam concentrate, or AFFF. This is a powerful type that works through a dual mechanism. It forms a robust air-excluding barrier, like the others, but its unique strength comes from also creating a thin, self-spreading aqueous film on the fuel surface that is capable of suppressing the evolution of fuel vapors.
A film, like a microscopic layer sealing the fuel.
Exactly. This film is a key differentiator. It provides rapid knockdown and vapor suppression. AFFF is also compatible with dry chemicals.
Okay, dual action. Film and blanket. What about FFFP?
Good one. Film-forming fluoroprotein foam concentrate, or FFFP. This ingeniously combines the strong physical blanket features of fluoroprotein foam with the rapid film-forming capability of AFFF. So it effectively deposits that vaporization-preventing film on the surface of a liquid fuel. It's also diluted to 3–6% solutions and compatible with certain dry chemicals, sort of the best of both worlds from that era.
Okay, combines the protein strength and the film, and then high expansion.
Right. For specialized scenarios, we have medium and high expansion foam concentrate. These are typically derived from hydrocarbon surfactants and are designed for specialized equipment to produce foams with very high volume ratios ranging from 20.1 up to approximately 1,000.1.
1,000 to 1. That's a lot of foam from a little liquid.
It's incredible. This equipment can be either air aspirating or a blower fan type, creating just a vast volume of light, airy foam. Ideal for total flooding applications in enclosed spaces, like basements or warehouses. And of course, the newest and increasingly prominent category is synthetic fluorine-free foam, SFFF, which we touched upon earlier and will definitely delve into in greater detail. Primarily due to those significant environmental and health concerns related to the traditional fluorinated compounds present in AFFF and FFFP.
Yes, FFF, the fluorine-free future. That's a deep dive into some serious specialized chemistry. What about storing these concentrates? Can you just mix different types or brands together, or are there strict compatibility rules?
Oh, absolutely not. And this is a critical safety point. A crucial rule states that different types and/or brands of foam concentrates shall not be mixed for storage unless you have clear compatibility data from the manufacturer that's accepted by the AHJ.
So no mixing unless proven compatible. Why is that so important?
Well, imagine the nightmare if, in the heat of a crisis, incompatible foams had been mixed. The entire system could be rendered useless. Incompatibility can severely impact performance, leading to a foam that simply doesn't form properly or breaks down instantly. Basically, it doesn't work when you need it most. Furthermore, the foam concentrate must be listed for use with the foam concentrate proportioning equipment and with the discharge devices in the system.
Listed for the equipment, too.
Yes, ensures all components work together as intended. It's a meticulously designed system, not just a collection of parts.
So specific phone for specific fires, specific equipment, and even specific storage conditions. It's truly a highly tailored solution.
It really is, and every detail matters. The concentrate must be listed for the specific flammable or combustible liquid to be protected. For water-miscible and polar flammable or combustible liquids, like alcohol-based fuels, alcohol-resistant concentrates are mandatory. Standard foams would just break down on contact.
Alcohol resistant. Okay, another specialized type.
And storage conditions are equally vital. Concentrates must be stored within their listed temperature limitations to maintain their chemical integrity. Storage vessels require clear markings identifying the concentrate type and its intended concentration, critical for quick, accurate response. And a detail often overlooked, storage tanks must accommodate the needed quantities plus extra space for thermal expansion to prevent tank damage from temperature swings.
Little details matter, like that expansion space.
Exactly. And another one, the suction inlet for drawing foam must be located a minimum of 1 inch, that's 25 millimeters, above the tank bottom. Any concentrate below this level is considered unusable.
Why is that? Sludge at the bottom.
Basically, yes. Ensures you always draw clean, effective concentrate, not sediment or sludge that might have settled out.
Okay. So we have this specialized liquid concentrate stored correctly. How do we transform it from that stored liquid into a mountain of fire-smothering foam? It sounds like a precise engineering feat involving proportioning and the right discharge method.
Exactly right. This is where the hydraulic and mechanical engineering really comes into play. Adductors and proportioners are the devices designed to achieve that perfect mix. They typically use the Venturi principle, remember that from physics. A drop in fluid pressure creates a vacuum to introduce a proportionate quantity of foam concentrate into a water stream.
The Venturi effect pulls the concentrate in.
Precisely. This pressure differential effectively draws in the concentrate from its storage. An inline adductor specifically meters the concentrate at a fixed or variable concentration right there between the water source and the discharge device. It's all about achieving that precisely calibrated blend.
You used a great analogy earlier about a soda fountain for firefighting. Can you describe some of the common proportioning methods they use to achieve that perfect mix consistently?
Sure. One common and very precise method is balanced pressure pump type proportioning. In the sophisticated system, a dedicated foam concentrate pump supplies concentrate at a pressure slightly higher than the main water supply. Then, a specialized controller, often using an orifice, precisely meters the concentrate. And a balancing valve ensures the foam concentrate pressure equals the water supply pressure, even at various flow rates. It's a delicate, automated dance of pressures to get the right blend every single time.
So it adjusts automatically to changing flows. Clever.
Very clever. Another method is the inline balance pressure, often called the bladder tank type. Here, water pressure is applied to a flexible bladder inside a tank, which then expends the foam concentrate into the proportioner. And a similar method is the pressure proportioning tank with diaphragm, where water pressure on a diaphragm displaces the concentrate. Different ways to use water pressure to push the concentrate out accurately.
That's a great image, that perfectly calibrated soda fountain for firefighting, precisely mixing the syrup, the concentrate, with the soda water, the water, to get the right blend for extinguishing a specific fire. And once it's mixed into that foam solution, where does it come out? How does it actually become the visible firefighting foam?
That's the crucial role of the foam discharge devices. These are the points where the foam solution finally becomes actual foam. Examples include familiar items like sprinklers, spray nozzles, and hose nozzles, but these are specifically designed or listed for foam application. More specialized devices include the foam nozzle or fixed foam maker. These are specially designed units that actively aspirate air, suck air in, and connect to a supply of foam solution to create the foam.
Aspirating air. So mixing air in is key.
Absolutely key for most foams, yes, especially low, medium, and high expansion. Then you have a self-adducting nozzle, which cleverly incorporates its own venturi to draw foam concentrate directly from a nearby supply through a short pipe or tubing. And for creating truly vast quantities of foam, there are foam generators, often the aspirator type. These fixed or portable generators use jet streams of foam solution to aspirate large volumes of air, which is then entrained on screens to produce foam, typically with expansion ratios of not more than 250.1.
250.1, still a lot of foam.
Still a huge amount. Each device is carefully chosen for its specific application and the type of foam it needs to produce, whether it's a dense blanket for a spill or that massive volume for total room flooding.
What's fascinating here is that even the most advanced foam needs fundamental support systems to work effectively, from the water supply that's the lifeblood of the system to the very pipes that carry it and the controls that manage it all. It's not just a product, it's an entire ecosystem of fire protection that needs to be perfectly synchronized.
Absolutely. The effectiveness of the foam system hinges entirely on the reliability and integrity of its supporting infrastructure. The water supply is truly the heart of any foam system. For deluge systems, it absolutely must be automatic to ensure rapid response. It needs sufficient capacity and a pressure to maintain foam and/or water discharge for the required duration over the entire protected area.
Capacity, pressure, duration.
The basics.
The absolute basics, but critical. A crucial concern, however, especially with this environmental shift we're discussing, is the pollution hazard introduced by the use of foam concentrate when drawing from public water sources.
Right, you don't want foam getting back into drinking water.
Definitely not. This is why cross-connections must be reviewed by public health agencies to prevent contamination. In terms of duration, water supplies generally must meet the fixed fire protection demand, plus an additional 250 gallons per minute, that's 946 lemon, for hose streams for at least 60 minutes, unless specific occupancy standards dictate otherwise.
An hour of operation plus hose streams. Significant water needed. It is. So not just enough water, but enough clean water for long enough with strict environmental considerations built in.
What about the pumps that get that water and concentrate where it needs to go?
Yeah.
They must be incredibly robust, right? Fire-grade pumps.
They must be. When automatic or manual foam system operation requires water or foam concentrate pumps, they shall be designed and installed in accordance with NFPA 20, which is the dedicated standard for fire pumps. This ensures their unwavering reliability and performance under duress. Then there's the piping and fittings. These must conform to the stringent requirements of Chapter 4 to ensure structural integrity and proper flow. And a listed strainer is absolutely essential in the water line upstream of the water valve. It protects the delicate proportioner and foam generator from debris.
Like a filter before the critical part.
Exactly. Don't want a pebble shutting down your multi-million-dollar system.
Good point. And I imagine the piping itself needs special consideration, especially in hazardous environments where it might be exposed to extreme heat or even physical damage.
Indeed. This is a critical area. Piping located inside dikes or within 50 feet, that's 15 meters, of undiked tanks must be buried under at least 12 inches, 300 millimeters of earth, or, if it's above ground, supported and protected against mechanical injury.
Buried or shielded. Makes sense.
It's a crucial defense against damage from explosions, impacts, even vehicle traffic. And for systems applying foam to a tank's liquid surface from the top, all piping within the dike or 50 feet of tanks must be designed to absorb the upward force and shock caused by a tank roof rupture.
Whoa, designed to survive a roof rupture. How do they do that?
It often involves clever engineering solutions like swing joints or specific bracing, things that allow flexibility, preventing the system from being torn apart during a catastrophic event like a boilover or explosion, and there are specific material requirements too. Unprotected carbon steel pipes shall not be used for foam solution piping in marine applications due to corrosion concerns. Also, foam concentrate piping shall not be galvanized.
No galvanized pipe for concentrate. Why not?
Galvanization can actually react with certain foam concentrates and cause serious performance issues, like gelling or breakdown of the concentrate. So plain steel or stainless is usually required.
That's an incredible level of detail just for the pipes, every component engineered for extreme conditions.
Yeah.
What about the brains of the operation, the detection and control systems? How are they designed for maximum reliability?
Well, for fixed systems, automatic detection is universally required, ensuring immediate response, though manual operation only might be permitted if approved by the AHJ for certain lower-risk scenarios. Detection must be by listed or approved methods or devices capable of detection and indicating heat, smoke, or flame, and installed per NFPA 72, the National Fire Alarm and Signaling Code.
NFPA 72, the alarm code.
Right. When a system activates, it must trigger a local alarm as well as an alarm at a constantly attended location. You need local warning and remote notification. And separate alarms are explicitly required to warn personnel of discharge and to indicate failures of supervised devices, distinct from the operational alarms.
So, different sounds or signals for foam coming versus system trouble.
Exactly. Clear signaling is vital for both immediate safety and operational awareness.
And I assume the power supply for all of this, especially the detection and control, needs to be incredibly robust and fail-safe.
Absolutely. Power supply reliability is paramount. The power supply for electrical detection systems shall be independent of the supply for the protected area.
So the fire can't easily knock out its own detection system power.
Correct. Ensures the detection system doesn't fail if the main power is compromised by the fire itself. For electrically operated medium or high expansion foam systems, the power supply must be as reliable as a fire pump circuit in accordance with NFPA 20, which sets a very high bar for continuity. Furthermore, all critical valves, main water, foam concentrate, foam solution for automatic systems shall be supervised in their operating position.
Supervised, meaning electronically monitored.
Usually, yes. Monitored to ensure they're open or closed as they should be. This includes supply, return, drain, and bypass valves, among others, to prevent accidental disablement or tampering. And finally, for medium and high expansion foam systems, strict minimum clearances from live electrical parts must be maintained, with specific adjustments required for altitudes exceeding 281 feet, 1,000 meters. Every single detail is considered to ensure these systems are ready, safe, and ideally impervious to the very hazards they're designed to fight.
So now that we understand the deep engineering and chemistry involved, where do these sophisticated foam systems actually get deployed? It's a surprisingly varied landscape, protecting everything from enormous fuel tanks to vital ships at sea.
Right, and this raises an important question. What fire hazards are we protecting against, and what type of system is best suited for that specific risk? NFPA 11 masterfully encompasses systems for a broad array of hazards, categorizing them primarily by the expansion ratio of the foam. That's the volume ratio of foam produced to the volume of foam solution used. It's really about matching the tool to the specific fire.
Okay, let's start with low expansion foam systems, covered in Chapter 5. Where are these typically found, and what kinds of fires are they best for?
Low expansion foams are commonly used for larger, more persistent fires. Things like storage tanks, fueling operations, and spill fires. That's what Chapter 5 focuses on. They create a heavier, more durable, and more flow-resistant blanket compared to higher expansion foams. For storage tanks, particularly cone roof tanks, those fixed roof tanks protection can be provided through foam monitors and hand lines, fixed foam discharge outlets for surface application, or even subsurface application.
Subsurface again, we'll get back to that. Any restrictions on fixed outlets?
Yes, a key one. Fixed outlets shall not be used to protect horizontal or pressure tanks. Their design just doesn't work well for those configurations.
Okay, now let's talk about that subsurface injection for tanks. It sounds like a radically different approach to getting foam onto a fire.
It really is a fascinating and highly strategic method. Foam is injected directly into the base of the tank, usually through product lines or dedicated foam inlets. It then rises through the fuel to form a blanket on the surface.
Rises through the fuel. Wow, what are the advantages?
Well, significantly less risk of equipment damage from an initial tank explosion or fire surrounding the tank. Your discharge points are low down, potentially protected. And critically, the ability to operate the system from a safe distance, enhancing personnel safety. The expansion ratios for subsurface injection are typically very low, between 2.1 and 4.1, because it needs to be dense enough to push up through the fuel.
Makes sense. Any specific notes on SFFs for subsurface?
Yeah, the standard notes that limited testing has been conducted with SSFs in subsurface applications. So checking with the specific foam manufacturer is absolutely essential here to ensure efficacy. It's still an evolving area for fluorine-free foams.
Good to know. What about those massive floating roof tanks, whether open top or covered, where the roof literally floats on the liquid? These seem to present a unique fire challenge.
They absolutely do. Most fires in these tanks actually occur in the rim seal areas, that gap between the floating roof and the tank wall.
The seal area. Okay. How is that protected?
Protection for these seal areas typically involves fixed discharge outlets specifically designed for that gap, foam hand lines, or sometimes small portable monitors. For full surface fires on floating roofs, which importantly are very infrequent and normally do not justify a fixed system because they are so rare and massive.
Rare, but potentially catastrophic if they happen.
Exactly. For those, emergency plans should rely on portable or mobile equipment. We're talking large capacity monitors, additional foam proportioning trucks, substantial water supplies. It's a major incident response. This is a scenario where mutual aid agreements and extensive pre-planning are paramount, as no single fixed system could realistically tackle such a vast, unpredictable event.
I recall you mentioned alcohol-resistant foams earlier when we discussed chemistry. Are those specifically for certain types of fuels and tanks, and why are they so specialized again?
Absolutely. These are a specialized and mandatory requirement for water miscible and polar flammable or combustible liquids. Think alcohols, ketones, esters, things that mix with water.
Why a mandatory? What happens with regular foam?
Standard foams would simply break down and become ineffective on contact with these types of fuels. The polar nature of the fuel essentially pulls the water out of the foam blanket, destroying it. So these AR foams, alcohol-resistant foams, require special engineering consideration. They often form a polymer membrane between the foam and the fuel, protecting the blanket. A key application technique is that foam should be applied as gently as possible to the fuel surface to prevent it from plunging through and mixing with the fuel, which reduces effectiveness.
The gentle application. Got it. Beyond the colossal tanks, low expansion foam must be critical for diked areas and spill fires where chemicals or fuels might accumulate, presenting a rapidly spreading fire hazard.
Indeed, foam monitor nozzles are frequently used for loading racks, providing flexible coverage for potential spills during transfer operations. For spill fires within a diked area, the potential spill area shall be estimated to determine the necessary protection requirements. Portable monitors, or foam hose streams, are generally considered adequate due to their flexibility in covering uncertain or changing spill locations. You can move them around.
Makes sense for a moving or spreading spill.
Exactly. The recommended strategy is systematic. Extinguish and secure one area, then move to the next section within the dike, systematically controlling the fire. Fixed low-level foam discharge outlets are also specifically designed to direct a compact, low-velocity foam stream onto the inner wall of the dike or directly onto the dike floor, minimizing disruption of the foam blanket and maximizing coverage.
Shifting gears, Chapter 6 covers foam water sprinkler and spray systems. This was one of the big consolidations in the 2021 edition, bringing over requirements from NFPA 16, wasn't it?
That's right, a very practical consolidation for designers and installers. Makes life easier. This chapter outlines detailed requirements for these integrated systems. They can be of the wet pipe, dry pipe, deluge, or pre-action type, offering versatility depending on the hazard and environmental conditions.
So similar types to regular sprinkler systems.
Pretty much, yes. Deluge systems are particularly applicable for two-dimensional flammable liquid hazards. Think spills on a floor with their primary purpose being rapid fire extinguishment over a wide area. Systems are designed to deliver foam to hazards for a specified period at given densities, sometimes before, sometimes after water discharge, depending on the system's specific design purpose.
And what about the actual sprinklers themselves in these foam water systems? Do they have unique requirements compared to just water sprinklers?
For the sprinklers, the standard is very particular about operational readiness. Requirements include having spare sprinklers readily available, scaled to the total number installed.
Always have spares on hand.
Exactly. So immediate replacements are possible. For example, you need at least 6 spares for facilities under 300 sprinklers, 12 or 300 to 1,000, and 24 for over 1,000. You also need to provide a sprinkler wrench and post a clear list of installed sprinklers in a cabinet. This list needs their identification number, SIN, type, thermal sensitivity, and pressure rating. Temperature ratings, classifications, and color codings for sprinklers are also meticulously specified in tables.
Wow, that's a lot of detail just for the sprinklers. Why so specific?
This level of detail isn't just for record keeping. It's about ensuring proper maintenance, enabling rapid repairs with the correct sprinkler, and ultimately ensuring the continuous readiness of the system. You can't just swap in any old sprinkler head.
Good point. The hydraulic calculations for integrated systems like these, combining water and foam, must be incredibly complex. You're dealing with 2 different fluid types almost.
They are, and precision is paramount. System piping must be hydraulically designed to obtain uniform foam and water distribution across the entire protected area. For wet pipe, dry pipe, and pre-action systems, 2 sets of calculations are actually required. One for the most hydraulically demanding condition balanced to the available water supply, and another for friction loss calculations using the Hazen-Williams method, typically. This ensures that even under the most strenuous conditions, foam reaches every required point at the correct pressure and volume. And importantly, when using alcohol-resistant foam concentrate, designers must consult the manufacturer for friction characteristics, as these can differ significantly from water or standard foam solutions, impacting flow.
Okay, so AR foams need special calculation attention too. What about the fire department? How do they interface with these sophisticated foam water systems without inadvertently compromising them?
Good question. If a fire department connection, FDC, is required, it must be installed on the supply side of the proportioner. But here's a critical safety point. A specific prominent sign is mandated right at this connection. It has to state, fire department connection. This connection feeds a foam water sprinkler system. Do not pump at pressures exceeding insert design pressure until foam liquid supply is exhausted. If incident is controlled by foam blanket, do not destroy foam blanket by excessive application of water.
That's very specific wording. Why is that sign so vital?
It's absolutely vital for a couple of reasons. First, it prevents overpressurization of the system by the fire department potentially pumping at too high a pressure, which could damage components. Second, and equally critical, it prevents the premature dilution or disruption of a nascent foam blanket by excessive water application from the FBC before the foam has done its job. That could severely compromise its effectiveness and potentially allow the fire to reignite.
So, clear instructions for the arriving firefighters. Crucial communication. Moving on to medium and high expansion foam systems, detailed in Chapter 7. These sound like they're for a different kind of challenge, entirely. Perhaps more about rapidly filling a large volume.
They are indeed. These systems are typically employed for total flooding applications in enclosed spaces. Think aircraft hangars, warehouses with rack storage, cable tunnels, places where you need to rapidly inundate a volume. Total flooding systems discharge foam into an enclosed space or enclosure around the hazard. Their fundamental purpose is to enable the required amount of fire-extinguishing medium to accumulate at the proper depth and to be maintained for a period of time required to ensure fire control or extinguishment. It's all about rapid, volumetric suppression.
So volume and depth are absolutely key here, not just surface coverage like with low expansion.
Precisely. For high expansion foam, a minimum foam depth of 2 feet, that's 0.6 meters, over the highest hazard, is required to ensure full coverage. When calculating the submergence volume, the total volume of foam needed to fill the space, the volume occupied by vessels, machinery, or other permanently located equipment, can be deducted.
You don't need to fill the space taken up by solid objects.
Right. Optimizes the design and prevents overestimation of the foam needed. The rate of foam discharge for high expansion systems involves highly complex calculations. It considers not just the submergence volume and time, but also the rate of foam breakdown by sprinklers, if they're present and operating, normal foam shrinkage over time, and potential leakage from the enclosure.
Wow, breakdown, shrinkage, leakage, lots to account for.
It's quite intricate. The annex even provides helpful example calculations for these scenarios because they can get complicated.
And once that foam blanket, or rather foam volume, is established, how long does it need to stay in place to be truly effective?
To ensure control or extinguishment, the submergence volume must be maintained for at least 60 minutes in unsprinklered locations and 30 minutes in sprinkled locations. This sustained coverage is absolutely critical for cooling things down and preventing reignition, especially in deep-seated fires.
What about highly specialized, intensely volatile applications, like for liquefied natural gas or LNG fires? These are known for their extreme cold and rapid flame spread. Can high-X foam handle that?
LNG fires are a unique beast. For LNG, the system design must be based on an analysis specific to the individual site, accounting for the unique characteristics of LNG, which is incredibly difficult to extinguish. Automatic alarms and actuation are generally required for fixed systems, unless a specific engineering study permits manual activation for very specific reasons. The discharge rate shall be able to achieve a positive and progressive reduction in radiation. That's key for LNG controlling heat radiation. But it's crucial to understand that high expansion foam will not normally extinguish an LNG fire, but it will reduce the fire intensity by blocking radiation feedback to the fuel.
So, control, not extinguishment.
Primarily control and protection, yes. Minimizing the impact, reducing the vaporization rate, protecting exposures, until other strategies, like isolating the fuel source, can be deployed.
Are there any fire hazards where these foam systems are actually not permitted or would be counterproductive? You wouldn't use foam everywhere, right?
No, absolutely not. It's vital to know the limitations. Compressed air foam systems, for instance, are explicitly not permitted on fires involving chemicals that release sufficient oxygen to sustain combustion.
Because foam works by smothering, cutting off air.
Exactly. If the fire brings its own oxygen, smothering won't work. Also, CFS shouldn't be used on energized, unenclosed electrical equipment due to conductivity risks, nor on water-reactive metals like sodium or potassium, which react violently with the water in the foam, or on liquefied flammable gas, where the application could cause unwanted turbulence or rapid vaporization. Applying foam in these specific situations could actually exacerbate the problem rather than solve it, turning a bad situation even worse. Knowing the don'ts is as important as knowing the don'ts.
Absolutely. That leads us nicely to compressed air foam systems, or CAS, detailed in Chapter 8. This was a newer addition to NFPA 11, wasn't it? What makes CAFS distinct from other foam technologies?
It was indeed introduced as a new chapter in the 2010 edition. It represents a distinct foam application technology that mixes foam solution with compressed air before it gets to the nozzle. These systems shall be designed and installed in accordance with their listing for the specific hazards and protection objectives specified in the listing. Listing is key here. What's truly unique and complex about KFS is that system flow calculation involves a mixture of both hydraulic and pneumatic elements. You have liquid and gas flow to consider together. This mixture must be addressed carefully to preserve the foam bubble structure until discharge. The quality of CFS foam is very dependent on that air solution mix.
Hydraulics and pneumatics together. Sounds tricky.
It can be, though notably for certain configurations, no calculations shall be required for a listed pre-engineered system design. That simplifies things for specific standardized setups, making them more accessible. Piping for CIFS is also installed in accordance with NFPA 13, the sprinkler standard, another example of how NFPA standards interlink and build upon each other.
Okay. Finally, what about low-expansion foam systems for marine applications, covered in Chapter 11? Firefighting at sea must have its own incredibly unique set of challenges and requirements, given the environment.
It absolutely does. Marine environments present highly specific challenges, from the corrosive salt water to the constant motion of the vessel, limited water supplies, confined spaces, the list goes on. This specialized chapter provides design information for low-expansion foam systems where required by the AHJ for marine applications. Its provisions were developed based on harmonizing NFPA standards with rigorous international regulations like SOLAS, Safety of Life at Sea, the IBC Code, International Bulk Chemical Code, and USCG, U.S. Coast Guard regulations, ensuring global consistency and compliance.
So meeting international maritime rules, what's the main purpose of these systems on ships?
The purpose is distinct. They're primarily intended to suppress or control tank fires involving a portion of the cargo area, assuming the tank top is open to weather, and critically, to provide protection for the crew while arrangements are being made to abandon ship. Safety of life is a huge factor here. Importantly, they are specifically not intended for incidents resulting from major explosions or collisions that cause the fire to exceed the area of the single largest tank. They recognize the limits of fixed systems in truly catastrophic scenarios.
So it's about containment, control, and crew safety in most situations, rather than full extinguishment in catastrophic events. And how long do these systems need to operate for, especially on a ship far from aid?
Foam concentrate must be provided to supply the system for a minimum of 30 minutes. For tankers transporting only hydrocarbons and using gas inerting of cargo vapor spaces, this duration may be reduced to 20 minutes under certain conditions. For deployment, 100% of the required foam application shall be by using one or two monitors located immediately aft of the protected area, ensuring concentrated coverage from a relatively safe position. Specific capacity requirements exist for these monitors based on the deck area they protect and minimum flow rates, like 330 GPM, 1250 Elman per monitor, often.
What are some of the truly unique aspects of marine systems, given that they're on a constantly moving vessel, often in harsh conditions?
Oh, there are several unique marine specifics. For instance, deck foam system piping shall be independent of fire main piping
Separate piping systems? Why?
to prevent a single point of failure. If the fire main is damaged, you still have your foam system, and vice versa. Redundancy. The system must also be meticulously arranged to prevent freezing, with exposed portions being self-draining or protected against freezing. Critical in cold climates or Arctic routes. Foam and water pump motors and controllers shall comply with IE 45 or equivalent, a rigorous standard specifically for electrical installations on shipboard, dealing with vibration, moisture, etc. And crucially, the standard acknowledges unique challenges like ships being subject to rolling, pitching, and yawing. This motion can cause sloshing of the burning liquid and reduced performance of the foam blanket.
Wow, the ship's movement itself affects the foam.
Exactly. So the system design must somehow account for that dynamic environment, something you wouldn't typically consider in a land-based application. It requires an entirely different layer of engineering ingenuity.
Okay, let's unpack this. We touched on it earlier, but there's a really significant, almost seismic shift happening in the world of foam, driven by critical environmental and health concerns. This isn't just about new regulations. It feels like a fundamental reevaluation of how we fight certain fires.
The profound global movement away from legacy fluorinated foams is indeed one of the most critical developments in fire protection right now. It's huge. These foams, like AFFF, ARAFF, FFFP, contain fluorinated surfactants that are classified as PFAS, per end polyfluoroalkyl
The
substances.
PFAS, the forever chemicals. We hear that term a
Yeah.
lot now.
Exactly. These forever chemicals have come under significant health and environmental scrutiny due to their persistence in the environment, their bioaccumulation in living organisms, and emerging serious concerns about their health impacts. The environmental persistence and health impacts of PFAS have completely changed how we view these once ubiquitous firefighting agents. It's transforming not just what chemicals we use, but forcing us to reevaluate every aspect of system design, training, discharge containment, even incident cleanup. The standard now explicitly states that the practice of dilution and release into the environment and/or wastewater treatment systems is obsolete and unacceptable for all fluorinated foams.
Obsolete and unacceptable. That's a strong, almost revolutionary statement for an industry standard.
It is. So this isn't just about new products. It's a wholesale change in acceptable practice, driven by this overwhelming scientific evidence and regulatory pressure.
What are the practical ramifications of this global shift? What's happening on the ground?
Well, as a direct result, international, federal, state, and local jurisdictions are rapidly limiting the use of legacy AFFF. Organizations like the U.S. Department of Defense, civil aviation authorities, they're implementing new strict restrictions. This is a top-down and bottom-up pressure for change, impacting everything from manufacturing to operational procedures. NFPA standards, being living documents, are being revised to address these trends and allow for flexibility in the future. However, the industry is still actively defining the criteria for environmentally toxicologically acceptable alternatives and the necessary rigorous testing metrics. It's a complex, ongoing process of research and development to find truly effective and safe substitutes. If we connect this to the bigger picture, you can clearly see the rapid shift to synthetic fluorine-free foam, or SFFF, as a key part of the solution. It's a testament to how quickly an industry can pivot when faced with overwhelming scientific evidence and regulatory pressure, but it's not without its challenges.
So, SFSS are the future. But are they a simple drop-in replacement for traditional foams? Or does this shift require significant re-engineering and rethinking of existing systems?
This is a critical point that many need to understand. Presently, there is no drop-in replacement SFFF for AFFF.
No easy swap.
No, it's not as simple as just swapping out one chemical concentrate for another in the tank. The entire system might need to be reevaluated. Existing equipment proportioners, discharge devices, even piping sometimes often requires reassessment to ensure compatibility and correct operation with these new foams. Each SFFF is unique. They lack common properties across different brands or formulations, and they cannot be used interchangeably without rigorous verification. This means facility owners and fire departments must work closely with manufacturers and engineers to ensure their systems are truly compatible and effective with these new, environmentally friendlier formulations.
So if the chemistry is fundamentally different, the performance characteristics must be different too. Can you highlight some key performance differences between SFFF and AFFF, especially regarding how they put out fires and how they're applied?
Certainly. Let's look at the core mechanism of extinguishment first. AFFF, remember, had two primary mechanisms: that thin, self-spreading aqueous film for rapid vapor suppression and the foam blanket to exclude air. SFFFs, however, rely almost solely on the foam blanket to seal in vapors and cool the fuel. This makes their performance highly dependent on the foam blanket's physical characteristics, its stability, its drain time, its ability to reseal, and the efficiency of the discharge devices used to create that quality blanket.
So the blanket quality is even more critical for SFFFs.
Arguably, yes. The way the foam is applied and its physical stability are paramount.
That's a big difference, relying only on the blanket. What about how long the foam stays effective on the fire? Its drain time. Does it last as long?
That brings us to drain time. This is interesting. AFFF typically had a relatively short drain time, often maybe 10 to 15 minutes, meaning the foam blanket needed frequent reapplication for continuous vapor suppression. This could lead to significant concentrate use over time. SFFF, when properly applied, often produces a more robust blanket that can remain effective for much longer, sometimes 30 minutes, sometimes several hours, depending on the specific foam and application. This can actually lead to lower foam concentrate use for sustained vapor suppression in many cases.
That's quite a reversal. You might intuitively think the newer foam would break down faster, so longer lasting blanket, potentially less concentrate used long term. Interesting. What about the physical application itself, how far it can be thrown, or how efficiently it aspirates air? Does SFFF travel as far?
This is another key area of difference: application range and aspiration. Many legacy AFFF systems used non-air aspirating nozzles, which resulted in an application footprint similar to a water-only stream, allowed for longer throws. Chapter 5 traditionally required increasing the application rate by 50% to compensate for wind and foam dropout, a practice originally developed for protein foams but applied to AFFF too. Large master stream non-air aspirated appliances could deliver AFFF effectively over distances of maybe 400 to 500 feet.
Pretty good range. How does SFF compare?
SFFF, on the other hand, when properly applied using handline and master stream nozzles, should have a higher air aspiration ratio. They need more air mixed in to perform optimally. This often results in them not traveling as far as a similar water stream application.
Huh?
The foam is lighter, more air filled. They also typically require that same 50% application rate increase for wind dropout. Large master stream air aspirated appliances can deliver SFFF effectively up to maybe 350 to 400 feet. Nozzles with an air aspiration factor of at least 8 to 10 are often recommended for some SFFFs.
So maybe slightly less range, and the type of nozzle, aspirating versus non-aspirating, becomes much more critical for SFFF performance.
Exactly. It highlights the need for specialized equipment and specific application techniques to ensure optimal performance. This is a major training consideration for firefighters adapting to these new foams. And, this raises an important question about how we validate these new technologies. It highlights the crucial importance of ongoing research and rigorous testing to ensure their effectiveness, especially since they behave so differently from what everyone was used to with AFFF.
Right. If they're so fundamentally different from AFFF, we need solid empirical data to trust them, especially for high-risk scenarios. Can you tell us about some of the cutting-edge research that's been done on fluorine-free foams? What are we learning?
Well, one key effort is the FPR-FNRL study, which is summarized in Annex H of NFPA 11. The Fire Protection Research Foundation, FPRF, contracted Jensen Hughes and the Naval Research Laboratory, NRL, to conduct a significant experimental program. This assessed the firefighting capabilities of various fluorine-free foams, FFFs, on both hydrocarbon fuels like gasoline and alcohol-based fuels. The study meticulously examined extinguishment times and burn-back resistance based on application rate, foam discharge density, foam quality, aspiration level, fuel type, and even the type of water used, fresh versus salt.
Wow, very thorough. Covering all the variables. What did they discover regarding different fuel types? We know fuels can behave very differently.
They did. The study yielded critical insights into test fuels. It found that heptane was shown to be the easiest of the test fuels to control and extinguish, basically serving as a baseline fuel. The findings then became more challenging. Mil-spec gasoline was found to be twice as hard to extinguish as heptane, and E10 gasoline, that's common gasoline with 10% ethanol, was twice as hard as mil-spec gasoline, which means it was 4 times as hard to extinguish as heptane for these FFFs.
4 times harder for E10 gas. That's huge. Shows how ethanol blends really challenge these new foams.
It absolutely does. It clearly demonstrates that not all fuels are created equal when it comes to FFF extinguishment, and the presence of ethanol, common in many modern fuels, presents a significantly magnified challenge that systems need to be designed for.
That's a stark difference depending on the fuel chemistry. What about the foam itself? Did its quality or how it was applied make a difference in performance during the tests?
Oh, absolutely. A major finding was the significant effect of foam quality and aspiration impact. The study showed that lower foam quality and aspiration rates caused a 20% to 50% increase in extinguishment densities required, meaning you needed significantly more foam solution per area if the quality wasn't good. This effect was even greater on alcohol-resistant foams.
So poor quality foam means you need way more of it.
Essentially, yes. This underscores a crucial takeaway for practitioners. It's not enough to just have an SFFF. You must use properly designed and operated equipment to achieve the optimal foam quality for effective extinguishment. The system and the application technique are just as important as the concentrate itself.
Beyond the lab and controlled tests, I know there's also been extensive field-scale testing to really push these foams to their limits in more realistic scenarios. Can you tell us about the IS fire testing? What did they find?
Yes, the IS fire testing, that's the International Association of Storage Tank Fire and Emergency Response, also summarized in Annex H3, conducted highly impactful extensive testing. This included both small-scale pan fires and crucial large-scale tests, including a 1080 square foot, that's 100-meter surface area, 36-foot, 11-meter diameter tank fire test.
A big tank fire test. That's getting real.
Exactly. They rigorously evaluated various application techniques, including forceful plunging application, semi-aspirating nozzles, fully aspirating nozzles, medium expansion devices, compressed air foam nozzles, and standard system pourers. And critically, they incorporated obstructions within the test area to simulate real-world scenarios, like internal tank pipework or structural elements.
Okay, so mimicking real-world complexity. After all that extensive real-world testing, what was their key conclusion? Were they optimistic about the new FFFs?
Well, IS Fire concluded that some FFFs are suitable for some applications, including hydrocarbon spill fires and smaller storage tanks, subject to validated testing of the specific foam and application device.
Okay, suitable for some applications with validation. That sounds cautiously optimistic.
It is promising and shows definite progress. However, they also identified a critical knowledge gap. They stated that a major gap in knowledge still exists in the application of any new generation foam to large diameter tank fires using large throughput monitors, especially non-aspirating types.
So the really big tank fires using the big non-aspirating monitors. Still a question mark for SFFFs.
It remains a significant challenge and area for ongoing research. This highlights that while significant strides have been made, more research and potentially different application strategies are still desperately needed for the largest and most challenging industrial scenarios, which often present the greatest risks.
So what does this all mean for how we manage foam discharges and ensure we're protecting the environment during and after a fire, especially given the ongoing concerns about PFAS from legacy foams and even understanding the impact of new SFFFs? It sounds like proper cleanup is becoming as complex as the firefighting itself.
It really is. Given the pervasive concerns about PFAS, the default method for disposing of legacy AFFF concentrate solutions and firewater runoff should be high-temperature incineration by an accredited environmental firm.
Incineration? That sounds expensive.
It can be, yes. It's not just a suggestion. It's becoming a critical part of environmental stewardship and regulatory compliance in many places. A significant challenge, however, is how clean is clean when decontaminating legacy equipment tanks, pipes, trucks that previously held fluorinated foams. The required cleanliness levels can be down in the parts per billion or even parts per trillion range. That necessitates rigorous testing and defined metrics. It isn't a simple rinse and go. It can be an incredibly expensive and time-consuming process to truly transition a system.
Parts per trillion. That sounds incredibly difficult and costly to achieve. What practical steps are being taken for containment measures during or after an incident to prevent environmental spread of any foam discharge, legacy, or new?
Right. During or after an incident, common temporary practices include things like blocking sewer drains to divert contaminated foam water solution away from waterways or treatment plants, deploying portable dikes for land-based operations, or using portable booms for marine-based operations to contain foam in a defined area. However, the standard notes that even with booms, as the foam bubbles drain, the foam solution itself, which carries the contaminants, PFAS or otherwise, may still spread underneath or through the boom, so containment requires active management.
So temporary measures help, but aren't foolproof. What about permanent solutions?
For facilities where conditions warrant, engineered containment systems are becoming crucial. These include things like dedicated holding tanks, open-top in-ground tanks, and sump and pump designs like lift stations, piped to above-ground or in-ground tanks. Critically, the standard advises that storing spent foam below ground is not advisable due to the potential for leaks, which could lead to severe long-term soil and groundwater contamination. Above-ground storage is preferred for inspection and integrity.
It truly sounds like preventing environmental contamination from foam is now almost as important as extinguishing the fire itself, an entirely new dimension to firefighting strategy and facility design. What about training? Can you still use actual foam for training exercises, given all these environmental concerns and the cost?
That's a very important question, and thankfully, the industry has found an elegant solution here. A valuable development is the availability of specially designed training foams from manufacturers that simulate firefighting foam but do not contain fluorosurfactants.
Fluorine-free training foams, okay.
These are typically biodegradable, have minimal environmental impact, and crucially can often be safely treated at local wastewater plants without requiring specialized disposal like incineration. They also often offer reduced burnback resistance compared to real agent, which actually allows for more repeat training evolutions with less fuel burned, making them a practical, cost-effective, and environmentally responsible alternative for preparing firefighters for real-world scenarios without discharging harmful chemicals.
Okay, so we have the right foam, the right system design. But before any foam can effectively suppress a fire, there's that truly crucial first step: meticulous planning and approval. It all starts on paper, right? Long before any pipe is laid or any equipment is installed.
Absolutely. What's fascinating here is that the entire foundation of reliable system is laid long before installation begins. All plans must be submitted to the AHJ for approval before installation or modification to an existing system. This step is non-negotiable. It ensures that the proposed design meets all local regulations, specific site requirements, and the stringent provisions of NFPA 11, and any deviation from approved plans shall require permission of the AHJ. Emphasizes the need for strict adherence, transparent communication, and constant oversight throughout the project.
So these aren't just rough sketches then. What kind of detail is actually required on these plans submitted for approval? It sounds like it goes far beyond simple diagrams.
Oh, these plans are incredibly detailed. They demand a comprehensive array of information to facilitate a thorough review by the AHJ. This includes things like the name of the owner-occupant, location, full height cross-section, or schematic diagrams, critical details of the water supply, including flow test results. You also need the make, type, and model of all discharge devices, a physical description of the hazard, including any hazardous materials involved, the exact type and percentage of foam concentrate to be used, plus the required solution application rate, specific submergence volume calculations for total flooding systems, water and air requirements for CFS, comprehensive hydraulic calculations, also identification and capacity of all equipment, the precise location of piping, detection devices, operating devices, auxiliary equipment, even schematic wiring diagrams and explanations of any special features must be included.
Wow, that is exhaustive. Leaves little room for error if done right.
Exactly. This exhaustive level of detail ensures thorough review, coordination among all parties involved: engineers, installers, owners, AHJ, and ultimately a system that is fit for purpose and fully compliant.
Once those incredibly detailed blueprints are approved, the physical work begins, bringing the system to life with exacting standards for every single component, from pumps to pipes to valves.
Precisely. The installation phase translates that detailed plan into a physical reality, and the standards are equally rigorous here. For example, for foam concentrate pumps with electric drivers greater than 30 horsepower, a full-service fire pump controller listed to UL standards is required. For diesel engine drivers, a listed diesel engine fire pump controller is needed. This guarantees the pumps, which are vital for delivering the foam, operate reliably under emergency conditions.
Makes sense. Need reliable power for the pumps. What about the valves, the control points that direct the flow of foam and water throughout the system? Any special installation requirements?
Yes. Manual controls for actuation and shutdown shall be conveniently located and accessible at all times, even during a fire, ensuring that personnel can operate the system safely if needed. Remote control stations are critically considered for large areas or where egress might be difficult to ensure operator safety and system activation from a secure location. In marine systems, isolation valves are absolutely critical in water, foam concentrate, and foam solution mains. They allow crews to isolate damaged sections for repair without disabling the entire system vital on a ship.
We discussed piping protection earlier, but it seems so important it's worth revisiting in the installation phase, given the extreme environments these systems often inhabit. Any key installation points for piping?
Indeed. As we discussed, piping inside dikes or near tanks must be protected against mechanical injury or designed to absorb rupture forces literally engineered to withstand explosions or impacts. And critically, remember, unprotected carbon steel pipe shall not be used for foam solution piping in marine applications due to corrosion. And foam concentrate piping shall not be galvanized due to potential reactivity. To facilitate future testing, specific valves and hose connections must be installed during installation to allow testing of proportioning equipment without full system discharge. This includes things like a pressure gauge connection at the most remote fixed foam discharge outlet and upstream of foam maker's chambers, allowing for accurate performance checks later on.
Okay, building in testability from the start. How do you ensure these complex systems, once installed according to plan, will work flawlessly when lives and property are on the line? Through rigorous documented acceptance testing, I'd imagine the final proof that it all works together.
Absolutely. Acceptance tests are a non-negotiable step upon completion of work. They're performed by the contractor and meticulously witnessed by the property owner or their agent. And, critically, all defects identified during testing must be corrected before the contractor leaves the job. This is the final verification that the system is built to standard and performs exactly as designed on day one.
What does acceptance testing involve? Flushing pipes, pressure tests.
All of the above. Before any foam goes through, all foam system piping shall be flushed after installation, using the system's normal water supply to remove any debris left over from construction. For compressed air foam systems, CCFS, piping is flushed with the system's air supply instead of water to prevent any adverse reactions or blockages unique to CSFS piping. Dry piping systems are pneumatically tested, pressure tested with air or nitrogen to ensure integrity, with specific limits on how much pressure can drop over 24 hours.
And then the big one actually testing the foam concentration.
Yes. The crucial operational and concentration testing takes place. For open deluge systems, foam solution concentration shall be verified by flow tests at the actual calculated discharge demand. You flow the system. These tests must be conducted with the pressure at the proportioning devices at the design operating pressure of the system. The percentage of foam concentrate injected must fall within the limits given in 12.9.4.1.4 Amsterdam, typically plus or minus a small percentage of the nominal concentration, or maybe not more than 1% absolute difference, confirms the proportioner is working precisely.
Okay, but given our earlier deep dive into the environmental impact of foam, especially PFAS, how do they conduct these acceptance tests without a massive, potentially environmentally damaging discharge of actual foam concentrate? That sounds like a major challenge for new installations.
This is where critical innovation comes in, addressing precisely those environmental concerns. Crucially, the standard now permits simulated foam concentrates or alternative test systems to be substituted for actual foam concentrate, if approved by the AHJ. This allows for system pressures and flows to be rigorously verified, confirming the hydraulics and proportioner function without discharging actual foam into the environment. It's a way to balance thorough testing with environmental responsibility. Similarly, full flow discharge tests for foam water deluge systems can often be performed using water only just to verify pipe integrity and flow characteristics.
That's a smart workaround. Test the mechanics without the environmental cost. Are there any specific signs or information required on these systems once they're installed and tested? It seems like critical details could get lost over time.
Yes, very specific signs are mandatory at system control risers. They act as essential, permanently marked quick reference guides for operators and maintenance personnel. There's a hydraulic information sign. This provides details like the location of the design areas the system protects, the required discharge density, the required flow and residual pressure at the base of the riser, discharge duration, and any hose stream allowance included in the calculation. Then there's a general information sign. This contains critical data for inspection, testing, and maintenance, ITM. Things like the facility name, occupancy or commodity classification, maximum storage height protected, typical aisle width, encapsulation details if relevant, presence of flammable liquids or hazardous materials, and crucially, the flow test data from the acceptance test. These signs must be permanently marked and weatherproof to withstand harsh industrial or marine environments.
Like any complex life-saving system, these aren't set it and forget it. Regular inspection, testing, and maintenance are absolutely vital to ensure they're ready the instant a fire strikes. This commitment to readiness must be continuous, right?
Absolutely. This raises that important question. How do we ensure continuous reliability over the life of the system? The standard provides minimum requirements for routine inspection, testing, and maintenance ITM of all foam and foam water sprinkler systems in the new Chapter 13. These aren't suggestions. These are non-negotiable activities outlined in the standard to maintain operational integrity.
What are some of the key maintenance frequencies? It must vary wildly depending on the component, from a simple valve check to something like overhauling a massive storage tank.
Indeed. If you look at Table 13.1.2 in Chapter 13, you'll find a detailed schedule of proactive ITM measures. For instance, every 10 years, foam concentrate tanks must be drained of foam liquid and flushed. That's a major task. The foam liquid may be salvaged and reused, but only after rigorous testing by the manufacturer or a qualified lab to ensure it hasn't degraded over that decade. After draining, the tank itself is inspected for internal and external corrosion and then hydrostatically tested to its specified working pressure to ensure its integrity. Water supply tanks also typically have a critical 10-year internal inspection.
That's a significant overhaul every decade, ensuring the very heart of the system, the storage tanks, are sound. What about more frequent but still substantial maintenance activities?
Sure. Every 5 years, the diaphragm of balanced pressure type proportioning valves must be inspected to ensure precise proportioning hasn't drifted. Foam concentrate pumps must be serviced in accordance with the manufacturer's instructions, but not less frequently than every 5 years. Could involve seal replacements, lubrication, etc. Pressure vacuum vents on atmospheric tanks also undergo a 5-year inspection and cleaning to prevent blockages that could impact tank integrity or foam delivery.
Okay, 5-year checks for key mechanical parts. What about annually?
Annually, mainline strainers must be removed and inspected and cleaned. This should also happen after each operation or flow test, ensuring no debris can obstruct the system downstream. The water supply itself should be flow tested annually to ensure its capacity and pressure are still adequate.
And what about routine visual inspections, the kind of things you might check weekly or monthly?
Routine visual inspections are ongoing. These include checking system piping and fittings for mechanical damage, for example, broken piping or cracked fittings,
Yeah.
which could compromise integrity during operation. Ensuring drainage facilities beneath foam water spray systems are not blocked and retention embankments or dikes are in good repair to manage runoff effectively. Components of proportioning systems, gauges, valves, signage, these are all subject to regular visual inspection, often quarterly or semi-annually. The big picture here is that regular, meticulous maintenance ensures reliability and proper operation. And this is becoming increasingly complex and critical with the introduction of new foam types and those stringent environmental considerations. It's an ongoing, unwavering commitment to safety and operational resilience. Hashtag, tag, outro.
You've just taken a deep dive into NFPA 11, peeling back the layers of a critical standard that defines fire protection for some of our most challenging industrial and marine hazards. We've journeyed from its essential purpose and continuous evolution through the intricate chemistry of foam concentrates, the ingenious mechanics of system design, the diverse applications across industries, and perhaps most importantly, the profound industry-reshaping environmental shift towards synthetic fluorine-free foams.
We've really seen how these complex, sometimes seemingly obscure standards are not just technical documents, are they? They're living safeguards. They represent a collective wisdom, constantly adapting to protect communities, industries, and now, more than ever, our planet. This unseen infrastructure of safety is working tirelessly, evolving to meet new challenges even as we speak, from, more volatile fuels to the absolute imperative of environmental stewardship.
Absolutely. The next time you see a massive fuel storage tank farm, or maybe a critical marine vessel like an LNG carrier, you'll know that behind the scenes, there's a highly engineered system guided by documents like NFPA 11, meticulously designed, installed, and maintained to protect it. It's really a testament to human ingenuity and foresight in the face of immense destructive power.
It truly is. And looking forward, as we continue to innovate and push the boundaries of materials and technology, how will the increasing demand for sustainable solutions continue to reshape not just firefighting methods, but also the very standards that govern safety, prompting us to rethink everything from chemical composition and system design to our long-held testing protocols? What new challenges and perhaps surprising solutions will the next edition of NFPA 11 bring as we strive for that crucial balance between safety and sustainability?
That's a powerful question to ponder, and one that drives innovation across the globe. Thank you for joining us on this deep dive. Stay curious, stay informed, and always remember the profound impact that standards like NFPA 11 have on making our world safer, more resilient, and hopefully more environmentally conscious.